Dr. Euler was solving mathematics in the M-theory laboratory spaceship when he came across a particularly difficult exact differential equation of this sort. In order to solve this, first we have to take the partial differential on this side, and since we have a dx, we're going to do the partial differential of y. So we're going to call that 3y squared plus 1. On this side, since we have the dy, we're going to want the partial differential in terms of x. So let's take the nx, which is going to be y squared minus 1. And if we compare these two, they're close, but they're not the same. So we have to find an integrating factor that's going to work to solve this. Let's try to find the integrating factor for x, so like mu of x. If we do that, then we're going to want e to the integral, and we're going to start with the nx minus my, and then we have to divide that by n because we're using the x version. So if we try to plug that in, what we're going to get is the integral of, well, nx is just y squared minus 1. Then we have to subtract the my, which is 3y squared plus 1. And then we have to divide this whole thing by n. And n is just going to be this original thing here, which is xy squared minus x dx. Now, maybe we could try to like simplify this stuff. So we'll have e to the integral. On the top side, we're just going to have a negative 2y squared. Negative 1 minus negative 1 makes minus 2. And then on the bottom side, we have x parentheses y squared minus 1. And here's the dx. We simplify this a little tiny bit more because we'll have minus 2 and then y squared plus 1 on the top divided by the x y squared minus 1 on the bottom. And this is supposed to be integrated, but it looks a little bit crazy here. We have all these y's. Like, sure, yeah, we could get the answer with this, but the problem is we're going to get something like e to the power of a whole bunch of y's, and then we'll have e to the power of some ln of x or something like that. But this is too crazy. Let's see maybe if we use the y version, and maybe that will help us out. Because if the integrating factor is too complicated, too crazy, then we can try the y version. So let's go and do that. Integral, obviously this is the same thing, and x minus my, this time is dy, but on the bottom, we're going to use the m instead of the n. So when we plug that in, we're going to do same stuff on top. In fact, I'll just jump over here because we know that the top is going to simplify to 2, negative 2 y squared plus 1. And then on the bottom side, though, we have the m, which is this. So we're going to put y to the third plus y, which is clearly going to be y squared plus 1, parentheses y. So we'll do something like that. Bam. And then now we can get rid of these. And we have something like e to the integral of negative 2 over y dy. Yay. So now this is actually going to work because now we can get something like e. And if we just solve this real quick, it's going to be negative 2 ln of y. Don't worry about the plus c, but we also have to put the negative 2 power up here. So we put negative 2 over here, and then we can cross off the e to the ln. And so we get that the mu of y is just 1 over y squared. So now we have our integrating factor. Well, that's pretty cool. Let's go over here, and now we're going to multiply both sides by 1 over y squared. So we have something like, I guess we'll just call it y plus 1 over y on the left side. It's going to be dx, and then we have plus, and we're dividing this by y squared, so we get something like x, and then minus x over y squared. And then this is going to be dy, and it's supposed to be equal to 0. Now let's just do a quick check to make sure that we take the partial differentials here is going to work out. Technically, this is going to be nx, so we're going to want like 1 minus 1 over y squared is going to be the nx. And over here, the my is going to be 1 and then minus 1 over y squared. And hey, look at that. Those two are the same. Therefore, this works out. This is exact. And now we can solve this. Now, in order to solve this, all we have to do is start by taking a look at fxy. We know that's going to be equal to the integral of this stuff right here. So we could just say y plus 1 over y, and then we're going to integrate that over dx. That's going to lead us to the fxy. So we're going to do something like xy plus x over y plus, and since here we're integrating over x, we're going to have some constant as a function of y. So like f is a function of y. So like what we're going to do is g is a function of y. And that's going to be equal to fxy, right? So now what we do is we could take a look at the f sub y, that's the partial y, which is essentially this. We've rewritten it. So this is actually our equation right here, just so we know. We've kind of rewritten this a little bit. But here's our fy. So we got x minus x over y squared. And that is supposed to be equal to the fy that we get over here. So when we take the partial of y over here, we're going to get something like x plus, or sorry, minus x over y squared. Just taking the partial derivative here. And then we have plus g prime of y. And those are supposed to be equal to each other. Well, that's funny. We have x minus x over y squared, x minus x over y squared, plus this g prime stuff. Well, clearly g prime of y is going to be equal to 0. And if we wanted to integrate this over dy, the integral of 0 over dy is just going to be c. Okay, so we just have c. Gy is equal to c. And if that's the case, all we need to really do now is plug it back into this equation. Gy equals c, so let's plug it in right there. We're going to get something xy plus x over y plus c equals f as a function of x and y. And here's where we have to remember what to do with this whole function of x and y. Keep in mind that it's going to be something that looks like a 3D structure, something like this, a little mountain, and we don't know what particular z point we're at. Okay, this is the z-axis right here. This is the function of x and y. It could be anywhere. But what we can do is we can set this axis to a particular point. So we're going to call it right here, we're going to call it c. I guess we'll have to separate these c's. We'll call that c1. This is going to be some other kind of c. So we'll call that c2. But what we've designated is that if we have xy plus x over y plus c1 is equal to z, and we just set z equal to c, or c2, then we have xy plus x over y plus c1 equals c2. And we've just chosen that particular z. We're allowed to just do that. But then what we can do is just subtract c1 from both sides, and then we essentially get our answer is going to be, I'll write it over here, xy plus x over y equals c, and I'll just leave it at c. So this equation was a little difficult because the integrating factor that we used the first time, mx, mu x, it was just too crazy. And it turns out that if that integrating factor is too crazy, you can actually use the other one, and sometimes that's much easier. Bam, look at that.